In engineering, things are always getting pushed and pulled by a whole bunch of forces all at once. So how in the world do we figure out the single, overall effect of all that activity? Well, today, we're going to find the one force to rule them all.
Right, I want you to imagine a big tug-of-war, but instead of two teams, you've got ropes pulling in all sorts of different directions. Where does that little flag in the middle actually end up going? And just how strong is that combined pull? That's not just a fun little puzzle, it's the exact kind of problem that's at the very heart of engineering and physics.
And you know what? The answer to that question actually has a name: the resultant force. It's the one single force that perfectly represents the combined effect of all the other forces put together. Finding this resultant is absolutely crucial for predicting motion and making sure our structures are safe and stable.
So here's our game plan for today. We're going to start with a classic method for combining just two forces, called the parallelogram law, and we'll walk through an example together. Then we're going to level up to a much more powerful technique that can handle any number of forces. By the end of this, you'll have a complete toolkit for tackling these kinds of problems. Let's get into it.
First up, let's grab our first tool from the box: the parallelogram law. This is a really fantastic visual way to understand how to combine exactly two forces that are acting on a single point, what we call concurrent forces. Okay, the official definition might sound a little textbooky, but the idea is actually super simple. If you just draw your two forces as if they're two sides of a parallelogram, starting from the very same point, the diagonal of that shape you create, that's it. That's your resultant force. It literally points you in the direction of the combined effect, and its length tells you the magnitude. And check this out. This image shows it perfectly. On the left, you see our two starting forces, P and Q. Then on the right, we just complete the shape. We draw a parallelogram. And that diagonal line, R, that's our resultant. It shows the exact path the object wants to take. See? Super intuitive.
Now, drawing pictures is great for getting the feel of it. But come on, this is engineering. We need precision. And lucky for us, a little bit of geometry gives us these two powerful formulas. The first one lets us calculate the exact magnitude, or strength, of that resultant force R. The second one gives us its precise direction, the angle theta. This is how we get the hard numbers. All right, theory is great, but let's put this into practice with a classic problem. We've got two forces pulling on an eye bolt. Our job? Replace those two forces with one single resultant force that does the exact same thing.
So here's the setup. We've got one force pulling with 120 newtons and another with 80 newtons, and they're both pulling at different angles. The big question is, where does the eye bolt actually feel the pull, and just how strong is it? Let's find out.
First things first, and this is key, we have to find the angle between the two force vectors. That's our alpha. We can see from the diagram that a straight line is 180 degrees. So a little simple subtraction gets us our answer, 105 degrees.
Okay. Now we just need to plug our numbers into that first formula. Our force P is 120, Q is 80, and the angle alpha between them is 105 degrees. I know the formula might look a little intense, but trust me, it's just plug and play. We substitute the values, and then we let our calculator do all the heavy lifting. And boom, there's our answer for the magnitude. The combined effect of those two different pulls is one single pull of 125.8 newtons. That is the total force this eye bolt is actually experiencing.
But wait, we're not quite done. We know how strong the pull is, but we also need its direction. So we use our second formula to find the angle theta. This tells us the direction of our resultant force relative to that 120 Newton force. The result? 37.89 degrees. And now we have the complete picture. Okay, so the parallelogram law, it's awesome. It's elegant, it's visual, and it's perfect for two forces. But what happens when things get messy? What if you have 3 or 4 or heck, even 10 forces all acting on one point? Trying to use the parallelogram law over and over again would be a total nightmare. We need something more powerful.
And this is where the method of resolution comes in. Honestly, this is a total game changer. The core idea is brilliant in its simplicity. You take every single diagonal force, no matter what its angle is, and you just break it down into two much simpler parts. How much of it is pulling horizontally and how much is pulling vertically.
Let's dive right into another example to see how this works. We're going to tackle a more complex problem, this time with 4 different forces all acting on a single point. This is really going to show off the power of this resolution method.
All right, take a look at this scenario. We've got forces pulling straight up, straight left, up and to the left, and down and to the right. Can you imagine trying to combine these two at a time with parallelograms? You'd be drawing all day. But with resolution, this mess becomes a simple, organized process. You know, the beautiful thing about this method is that it's like a recipe. You just follow these 5 steps every single time and you'll get the right answer. First, you resolve everything, then you add up all the horizontal bits, then you add up all the vertical bits, and finally, you use some basic geometry to get the final answer. It's a foolproof plan. A table like this is the perfect way to organize the chaos. We take each force, one by one, and use some simple trigonometry to find its x and y parts. So for that 300 Newton force, for instance, we use cosine to find out how much of it is pulling to the left, and sine to find out how much is pulling up. The key here is being super careful with our signs. Right and up are positive, left and down are negative. Get that right, and you're golden.
All right, the hard part's over. Now it's just some simple addition. We just add up all the numbers in our x component column to get the gram total for the horizontal force. That's our sigma Fx. Then we do the exact same thing for the y column to get our sigma Fy. Easy.
And hey, does this look familiar? It should. We've turned that whole complicated mess into one net horizontal force and one net vertical force. They form a perfect right-angled triangle, and our final resultant, r, is just the hypotenuse. So we plug our two sums into the Pythagorean theorem to find it.
And there it is. All that mess, all those different forces pulling in every which way, boils down to one single force of 431.8 newtons. We've taken a really complicated system and found its simple, elegant truth. That's the power of this method.
Okay, let's just take a breath. We've just added 2 incredibly powerful tools to our engineering toolkit for finding resultant forces. The real trick, the mark of a great engineer, is knowing which tool to pull out for which job.
So let's break it down. The parallelogram law is your scalpel. It's visual, intuitive, and absolutely perfect when you're dealing with just 2 forces. The method of resolution, that's your powerhouse, your Swiss Army knife. It's a step-by-step, algebraic process that can handle any number of forces you can throw at it. It's systematic, it's scalable, and it will never let you down.
So we've totally mastered finding the single result of all these forces. We know where things are headed. But let's flip the question around. What if you wanted the exact opposite? What if you wanted to add one more force to the system? A single force that would create perfect balance and bring everything to a complete standstill? Well, my friends, that is the question of equilibrium, and that's a topic for another explainer.